Today we're going to be going over the concept of equilibrium in chemistry. So hopefully you guys are ready. So we can have normally reactions. This is a balanced reaction of basically just creating water, right? So you have 2H2 plus O2 yields 2H2O. So there's 4 hydrogen atoms, 2 oxygen atoms on each side. And you can also write it as the decomposition form, which is 2H2O yields 2H2 plus O2. So it's basically the same thing, just the other way around. And these are basically the same thing, right? I mean, obviously the opposite things are happening, but it's involving the same exact species. Well, a way you can actually write it so that both are kind of taken into account is in equilibrium. So 2H2 plus O2 yields, but also backwards yields 2H2O. So this sort of symbol just means it's in equilibrium, which means that the rate of the forward reaction is the same thing as the rate of the backwards reaction, which basically just means that, well, chemical reactions are sort of ongoing things, right? They don't just go, all of them don't just go and necessarily stop. Some are, going constantly, and, things are constantly moving around and reacting in the world. And so that's kind of how you represent that. And in this situation, it means that the rate of the forward reaction and the rate of the backwards reaction are the same. But it doesn't necessarily mean that the concentrations of everything are the same, right? There could be more of this, and there could be less of this, but the rates of moving and converting into product is the same as the product converting into reactant. So the rates are the same, but the concentrations don't necessarily have to be the same. And if they are, that's generally just a coincidence. All right, so take the same reaction we wrote. Normally, when we talk about the equilibrium constant, it's basically a measurement of the concentrations of a reaction at equilibrium. So what we do is we take each product, right? So in this case, our only product is H2O, and we put it to the power of the amount of moles there is. So in this case, there's 2 moles, so we square it. And we put that over the reactants, every single reactant, and do the same thing with the exponent, move all the moles to the exponent of the reactant. So in this case, O2 has no exponent, so we just put that, and H2 has an exponent or a mole number of 2, so we put the 2 there. So our K is equal to H2O squared over H2 squared times O2. So this is just products and reactants, same thing we were just looking at. And if you notice, if you add more to the products, since it's products over reactants, the K actually will increase, right? Because you're basically adding more to the numerator of the fraction. But if you make the denominator bigger, right? If you make the denominator bigger, even like a normal division equation, the eventual, answer, your quotient is going to be different. It's going to be smaller, because you're making the denominator bigger and you're not affecting the numerator. So you're dividing it by more. All right, so this might look a little bit complicated, but this is just basically a way to represent equilibrium. So the lowercase letters are just the amount of moles of each substance, and then the uppercase are just the substance themselves. So we can see in this reaction, AA plus BB yields CC and DD. The equilibrium constant is 10, K. And in this one, it's basically what you're doing is you're multiplying everything by 2. So you're basically just doubling the entire thing. And in equilibrium, what you actually do to your equilibrium constant is you square your equilibrium constant. I know it might make sense if you were to times your equilibrium constant by 2, but if you think about it, the reason you square your equilibrium constant and you do it to an exponent instead of just multiplying it is because what you're doing when you're manipulating a reaction is you're including everything in the reaction. You're not just doubling one thing, you're doubling every single thing. And if you double single thing, it's going to become exponential, and it's going to increase at a rate of 10 squared instead of just 10 times 2. So your K is going to become 100. So it's just another example. This is a little bit different. So when you reverse a reaction, normally if you were to be working with some other sort of thing like Hess's law, which is something else I'll make a video on, you would normally multiply it by -1 when you flip the reaction over. And in this case, instead of multiplying it, you just do to the power of -1. Because here all you're doing is you're just reversing the reaction. You're flipping everything on its head. So the products in this one are CC and DD, and the products in this one are AA and BB, and respectively, they the other products of the other one become the reactants of the new one. And yes, your K is going to be equal to 10 to the -1 instead of just 10, which is the same thing as 1/10. All right, so when you're actually looking at your equilibrium constant as well, there's a way to sort of tell like which side is favored. So if K, for example, since it's products over reactants, if K is humongous, a humongous number, that means there's probably more products. That means there's definitely more products because products over reactants is bigger, which means products is bigger if K is huge. If K is tiny, remember K is never going to be negative because you can't actually have a negative concentration. But if K is a really small number, that means there's probably a very, very, very large number on the bottom, right? Which means that there's a very, very large amount of reactants and not so much of products. So that's kind of how you know which side's favored. So if there's K is bigger, the products are favored. If K is smaller, the reactants are favored. All right, so let's just look at an example. So say you have a reaction at equilibrium and they give you the concentrations of each thing at equilibrium. So 0.1 molar at equilibrium, 0.2 molar at equilibrium of O2, and 0.3 molar at equilibrium of H2O. So what you do in this case is you write out your equilibrium constant, and what you're trying to do here is calculate your K. What you do is you write out your equilibrium constant, you plug in the respective values. So for H2O you put 0.3, for H2 you put 0.1, and then for O2 you put 0.2. You make sure to keep putting the square and all that. And you basically, from this, you just kind of ignore the molar, right? Because they're going to cancel out. And you sort of just do the math. And so 0.3 squared is going to be 0.09, 0.1 squared is going to be 0.01, and 0.2 is just going to stay as 0.2. So you're going to have 0.09 over 0.002 when you multiply these two out, which is going to equal to 45, which is going to mean that K is equal to 45. And remember, in this case, this means that your reaction is going to basically favor your products at equilibrium, right? Because K is greater than 1, which means it's going to probably be more products than reactants.